Enjoy the session.
Okay, welcome to the second genome session. We'll have today three interesting talks, and so the first one is going to be Lian Rongpu, and she's going to talk about 3-CAC improving the classification of phages and plasmids in metagenomics assemblies.
Okay, so thank you, Tommy, for your introducing, and thank everyone for being here. So today I will present a recent work collaborated with my advisor, Long Shamir. We developed a 3-CAC tool for metagenome classification. It's able to classify both phage and plasmid from metagenome assemblies. So here is the outline of the talk today. I will briefly introduce the background of this problem and show the existing classifiers, and then I will introduce what's new in our new 3-CAC algorithm, and we will benchmark it on both simulated and real sequencing metagenome assembly, and in the end, I will show the challenge and the future plan for this project. So in metagenome assembly, researchers collect samples from diverse environments, and then they use sequencing technique and assembly to reconstruct the genome and get to understand what species contained in the sample as well as their function. So after we do metagenome assembly, we get a mixed metagenome assembly. Then the first problem we need to answer is who are they? What are the species contained in the sample? The metagenome of the microbiome community usually contains bacterial chromosome and the plasmid and the phage. And the genome of plasmid and the phage are usually small and circular. And the interesting point is those small circular genomes, they can move between different species in the microbiome community, and thus they can help to transfer genetic materials between different species. So that's why they are important, and that's why we care about them. So the problem of identifying such mobile, since they can move between different species and they can also carry genetic materials, so they have another name called mobile genetic elements. And the problem of identifying those mobile genetic elements is very critical for us to better understanding their function in the microbiome community. So today I will introduce how existing classifiers classify those mobile genetic elements and introduce what's new in our algorithm. So for existing classifiers, they can divide it into two main categories, reference-based or reference-free. And for reference-based method, they map the context to a non-reference database, and then they get to know which genome each context came from based on its similarity to the non-reference database. Those classifiers usually have high precision but very low recall because the non-reference database is incomplete. And additionally, those classifiers are time and resource intensive when the data set increases. So recently, several reference-free classifiers will come out. So given a context without using the non-reference database, how can we know which genome this context came from? And before I introduce the reference-free classifier, I would like to introduce what is the composition information of a context. So given a context, the composition information of a context means the frequency of different chemers in this context. So the right figure shows the thermal composition of this context. We can calculate the composition information by scanning the context from left to right and get the chemer in each position. And then we calculated the frequency of each different chemer and normalize the frequency by the total number of chemers in this context. So all the reference-free classifier, they assume that different species have unique composition information. So they use machine learning models to learn the chemical composition information for different species in the reference genome, reference database, and then given a new contig, they will classify this contig according to its composition information. So currently, plus class and plus flow are two plasmid classifiers based on machine learning and composition information. They can classify a contig into either chromosome or plasmid. And also, there are phage classifiers that can classify a contig into either phage or chromosome. Deep Biofinder is a reference-free phage classifier, and Biosorter is kind of reference-based phage classifier. But however, both phage classifier and plasmid classifier, they are binary classifier. And as we introduced in the beginning, both phage and plasmid are commonly found in the metagenome, metagenome community. So for a phage classifier, if we give the plasmid contig, what will happen? They will randomly classify the plasmid contig into either phage or chromosome. So significantly, those binary classifiers are not good enough for metagenome classification. And recently, there are two three-way classifiers, viral verify and PPR method, were proposed. They can classify both phage and plasmid from the metagenome assembly. But however, when we test viral verify and PPR method on simulation data, we find that both of the tools can distinguish phage well with plasmid, but in the phage classification and the plasmid classification, there are a lot of false positives come from chromosome. And the reason behind it is because in the metagenome assembly, the data set is imbalanced. Chromosome contig dominated in metagenome assembly, so around 80% of contig in the metagenome are chromosome, and the phage and the plasmid usually only account for 20%. So even a classifier has equal prediction ability for each class, when the testing data set is imbalanced, then the low false positive in the major class will cause large false positive in the minor class. So that's result the low precision in phage and the plasmid classification. And to solve this problem, we came out of the idea is actually you see for the phage classification, most of the contamination from chromosome. So it looks like we can use the binary classifier again to filtering the chromosome in phage classification. And similarly, we use a plasmid classifier to filtering the chromosome contamination in plasmid classification. And now the classification looks much more clean. But however, those machine learning-based classifiers still have some limitation. They only show such reasonable performance on long contig. So if you give them all the contig, then here is their performance. They perform very poorly on short contig. So before I introduce how we improve the classification of short contig, I would like to remind you how we assemble read to contig in metagenome assembly. In metagenome assembly, people use assembly graph to assemble the read into contig. And in the final step of assembly, the output is the assembly graph, and each node in the assembly graph is a contig, and each edge in the graph connected to contig with overlapping sequence. So it means two contig with edge may come from same genome. However, for all the existing classifiers, they ignore the connection information and they classify each contig independently according to their composition information. So let's remember the connection information between contigs may be variable for the classification, and this is the innovative point in our 3CAC algorithm. So here is the motivation of 3CAC algorithm. We project the classification to the assembly graph, and the left, this is the result in a simulation data. The left graph shows the result of viral verified classification, and the right graph shows the ground truth. And the three colors in the graph respectively represent chromosome, plasmid, and the phage. So in these two graphs, we can get a conclusion. The proximities in the assembly graph can help to assist the classification. So here is the pipeline of our 3CAC algorithm. Our input is the assembled contig in metagenome assembly as well as the assembly graph. And the first phase of 3CAC is use three-way classifier, viral verifier, or PPR method to do three-way classification. And as we know, there are high contamination in phage and the plasmid classification from chromosome. So we further use phage classifier and the plasmid classifier to filtering chromosome contig in the phage and the plasmid classification. Then we get an initial classification with high precision in long contig. And then we project, in the second phase of 3CAC, we project the classification to the assembly graph, and then we use the connection information in the assembly graph to do correction and propagation. I will show more details about correction and propagation in the following slides. So here is an assembly graph with the initial classification of 3CAC based on viral verify, and I will show how we do correction. In the correction step, we check for each classified contig in the assembly graph. If the classified contig has more than one classified neighbor, and all the classified neighbors are with same class, but this contig was classified into a different class, then we think this contig may be wrongly classified. We will correct its class to be same as its neighbors. And after we do correction step, we will check for each unclassified contig if they have at least one classified neighbor, and all of its classified neighbors are belong to the same class. Then we will propagate the class of its neighbor to this contig. And here is the result after we doing propagation step. We can see the result is very similar to the ground truth as we showed previously. So here is the data set we use to benchmark 3CAC and other existing classifiers. We have 4 simulation data set with different complexity, and both from short read and long read technique, long read sequencing technique. And we also have 2 real sequencing data from the human GANT sample, also with both short read sequencing technique and the long read sequencing technique. And one thing you need to notice is that for SIM1 and SIM2 that are assembled from short read, more than half of the contig are shorter than 1,000 base pairs recorded as short contig. And if you remember it, in the previous slides, I mentioned all the machine learning-based methods perform very poorly on those short contig, but those short contig account for more than half of the short read assembly. Here I will show the improvement of 3CAC by the raw classification number. So in the top table shows the classification result of viral verify and the PPR method. So for example, let's see the red column. It shows the phage prediction in viral verify. So we can see around 200 chromosome contig were wrongly classified as phage by viral verify. It means viral verify only have precision around 0.5. And after we applying the phage classifier to filtering the chromosome contig, now we can see the false positive from chromosome reduced from 200 to around 70. And after we use the correction and the propagation step in the assembly graph, now we can see the record of phage are significantly improved from 250 to 650. Before I show the final result of 3CAC, I would like to emphasize the performance of the second phase of 3CAC by using the assembly graph. Here we show the record and the precision by the contig length, and we show 2 simulation data assembled from short read assembly. And the dashed line shows the initial classification of 3CAC, and the solid line shows the final classification of 3CAC, and the blue color shows result based on viral verify, and the red color shows the result based on PPR method. So we can see the recall are significantly improved in the top, while the precision are similar in the bottom. And now let's pay attention to the contigs that are shorter than 1,000 base pairs. As we remember, more than half our contigs are short contigs, and the recall for short contigs were improved from below 0.2 to around 0.8, while the precision is similar. So this figure shows that the second phase of 3CAC can significantly improve the recall without loss of precision. And here is the final result of 3CAC. We show the performance of 3CAC and the viral verify and the PPR method on the 4 simulation data set. The blue bars shows viral verify and the 3CAC based on viral verify solution, and the red bars shows PPR method and the 3CAC based on PPR method solution. So we can see 3CAC based on viral verify and the PPR method has comparable result, and they always perform best in precision recall and F1 score in all these 4 simulation data set. And SIM1 and SIM2 are assembled from short read, and SIM3 and SIM4 are assembled from long reads. So we can see the improvement in the short read assembly is more significant than in long read assembly. And here we show the performance on the real sequencing data from human GANT samples. The left figure shows short read assembly, and the right figure shows long read assembly. On long read assembly, we still can see the 3CAC based on viral verify or PPR method have comparable result, and they perform better than PPR method and viral verify. But when we see the short read assembly, we can see 3CAC based on PPR method has the best performance, but 3CAC based on viral verify performs slightly worse than PPR method. We do further analysis, and we find the reason is that around 60% of contigs are isolated contigs in short read assembly, while this percent is only 20% in long read assembly. And if you remember it, when we used the assembly graph to improve the recall, it only works for non-isolated contigs. For the contigs that are isolated with no neighbor in the assembly graph, the second phase of 3CAC cannot improve it. So to track the ability of 3CAC, we further track the performance on non-isolated contigs, and now we can see 3CAC still performs best in short read assembly, and 3CAC based on viral verify or PPR method have comparable results and performs much better than PPR method and viral verify, and the improvement is still more significant in short read assembly than the long read assembly. So that's our result, and here is a conclusion. Is the key technique behind the 3CAC is we using the adjacency information in the assembly graph, but the challenge is for the isolated contigs, they have no neighboring information. How should we improve the classification? And when we do benchmark in real sequencing data set have no gold standard. Learn how to set gold standard is also very challenging. And currently in our pipeline, we didn't use the coverage and the length information of contigs. So in our future work, we would like to combine those information and see if we can further improve the result. And also in the current pipeline, when we scan the contig in the assembly graph, in the correction and the propagation step, we scan it randomly. So in the future, we would like to consider more about the order and see if we can improve the result by use maybe more sophisticated order. So that's all. Thank you for your attention, and any questions?
Thank you. We have questions. One here.
So you showed us that you take the results of the classifier and you then assign them to the nodes of the graph. Then the classifier, I guess, also outputs some probability or certainty or uncertainty of the classification.
Yes.
So I wonder if you thought about using this information, because currently it seems that you are taking it as a hard decision. classification to each of the classes? And then also another question, did you think about taking the results after correction and then improving the classifier, given that you improved the prediction? So could you retrain the classifier to improve its performance?
Yeah, thank you. It's a good question. So for the first question, actually, we need to consider it, but I didn't show the details here since the time limitation. Yeah, for the classifier, some of the classifier, they will just give you label, plasmid, or chromosome. Some of the classifier, they give you probability score. So for classifier, when they, like for plus class, they give you probability score, and usually people classify contain larger than 0.5 as plasmid and lower than it as chromosome. But in our pipeline, in the first step, we want to make sure high precision, so we set the score to be more strict, like we need to be larger than 0.7 as plasmid and lower than 0.3 as chromosome. And for the contact between them, they are uncertain. We will leave it for the second step of 3CAC to classify it according to the connection information in the assembly graph. Yeah, thank you.
Hi, I got two questions. So first one is, do you have an implementation of this method available? Can I use it?
Excuse me?
Sorry? Is your method available online?
Yes, of course, sorry. I didn't show it, but you can contact me later after the talk. It's available on GitHub, and the paper, of course, is also available online, so I can give you details after the talk.
Great, thanks.
You.
And my second question is, so that was partly addressed, but do you have any insights other than, those isolated contexts where the performance of your method is not, it's in the 80–85% range? What is the source of still those errors?
So in the simulation data, the percent of isolated contact is low, but in the real sequencing data, especially in short assemblies, the percent of isolated contact is very high. I think it is limited to the current short sequencing technique, since for short read, they are usually with length below 300, so the assembly is very fragmented, so they have a lot of short and isolated contact. Yeah, and so that's our next step, since they also account for a large portion in the metagenome assembly. We need to consider how to improve this part. But in the other hand, since a long read assembly is become more available recently, so maybe we can just more focus on long read assembly.
Yeah, great. Thanks.
Thank you.
Okay, we have to move on. So we thank again Liang Rong. And the next talk is a highlight talk. And Alina Frolova is going to present the MetaSub study, so the microbiome, a global map of the microbiome, the urban microbiome around us.
Hello, everyone. I'm super excited to be here, and thank you, organizers, for giving me such an opportunity. And I actually want to appreciate the previous speaker, because it's so much easier to talk about metagenomics after the major concepts were explained. So this is the highlight talk, and I want to tell you about our metagenomics atlas, which took us maybe 5 years to finish and publish. And even though we didn't get to the cell cover, I still want to commemorate this wonderful image created by our first author, David Danko, who tried to kind of squeeze the concept of the study in a single image. So we profiled almost 5,000 samples from public mass transit systems. It was the whole genome sequencing from 60 different cities, collected over 3 years. We found lots of interesting information, and yeah, this is a very huge study, so our authors list is quite extensive, but I'm especially proud that we included MetaSub consortium in the end, because if you go to the paper, you still can click, it will expand, and you will read lots more names. And I'm really proud that we acknowledge everyone, like any volunteer that helped us to collect the samples. But since you since you can read this paper online easily, I really want my talk to be is kind of a story, why we started it and where it has led us. So if you go back to 2015 to New York, to Chris Mason. He's a scientist from Weill Cornell Medicine, and he was taking his daughter from the kindergarten. And you know, little kids, they try to lick different surfaces or put different objects in their mouths. And as a parent, Chris maybe wanted to stop her, but as a scientist, he thought, is this really harmful? What is there? Should I really stop her? And apparently, a few years later, he was advising people to roll their children over the floor in New York subway. Yeah, and around that time, also very, very nice book was published, each from two wonderful scientists who got really fed up of their friends asking about how they should raise their children. A book is called Dirt is Good, apparently for developing the immune system of your children. But when I checked the reviews on this book, I found very, very common pattern you can read there. And apparently people expect us to give black and white answers, but this is not what science is supposed to do, because we know that some species are pathogenic because we grew them in a lab in artificial environments, but are they really harmful in a built environment, for example? This is what we wanted to check. So Chris conducted a pilot study in a New York subway. He collected around 1,500 samples, and what they found, first of all, is that half of the species in each sample is unknown. And the rest is bacteria, which are like mostly harmless. And they could even able to track some events many years in the past, as it was with one subway in New York, which was flooded because of the Hurricane Sandy, and they could still see marine environment there. So Chris didn't stop, and he created a MetaSub consortium to basically put this research on a global level, and every year, on the June 21st, we have Global City Sampling Day, where all metasubbers all over the world starting to swab different surfaces in the subways or other public mass transit systems. And this is actually a super exciting day for us. We have lots of very funny stories from there, and we actually try to educate public, because this is type of a study which you can really easily combine with citizen science, and I think this is really important. We need to really connect to the regular people to explain them what they can see around them. And I'm part of the MetaSub since 2016, I think, and since then I'm organizing and leading MetaSub Kyiv Hub in a very, very wonderful city, which I love the most. We also have lots of funny stories. Like here, our students is extremely sad that we have to stop sampling at that day. And another story we had was one of the stations where I was also present, and I was seeing at the back of my head that policeman is coming to us. And I thought, oh no, he will ask us to stop, because the subway in Kyiv is strategically important object. So even though we had the permission, sometimes they ask you to stop, but it was opposite. He got really interested in what we were doing, and he got really excited, and he told us, you need to come and swab our interrogation room. The thing is that on every station we have like a small police unit, so if they catch some suspicious people, they put them in this interrogation room where they wait. That's why you can see the like cuff hands there. So the highlights. First of all, we found out that there is the consistent core microbiome from 31 different taxa, and that antimicrobial resistant genes are really widespread in the cities, and we found like many novel bacteria in viral species. But what is urban microbiome actually? In the pilot study here, Priest found that it's kind of closely resembles skin microbiome, but later in a follow-up paper, when we studied air microbiome in different cities, you can still see that it can be true for some cities, but for other cities, they rather resemble, for example, soil microbiome. So in the main paper, we rather think that it's neither soil nor skin, And of course, we can actually see a trend if we study the surfaces which are oftenly touched by people. It is actually resemble skin microbiome, but it's not necessarily like that. And even with the most relaxed constraints, we still found on average 40% of the samples being unknown DNA. So it's either a unique microbiome for this urban environment, or maybe it's still a part of the commensal microbiome or the soil microbiome, which we still want to answer in the future because we still continue the study. We collect samples every year. In terms of AMR genes, is resistant to particular drug classes. The most prevalent one was MLS, but in terms of abundance, if you compare it with the housekeeping genes, for IMR genes, it was from 0.1 to 10 RPKM, while housekeeping is 10 to 100, so they are not really abundant. However, we found some samples in which we found lots of IMR genes, even though not abundant. It means something might have happened in the environment that led to the sample having lots of AMR genes. And the most frequent question we actually have is, which is the most dirty city in the world? But I think it's a little bit ethically incorrect to answer that, because even based on like IMR profiles, they are super diverse, and it's not always correlated with like a density with the density of the population. And to give some kind of an instrument for external people to try to compare our data set with what they are doing, we also created MetaGraph, which is ultra-scalable framework for DNA search, alignment, and assembly. And we have here the web interface. You can, if you study something novel, you can input your organism genome in the search field, and you will get an answer in seconds whether there is something similar in our metasub samples. In terms of microbial signatures for the particular cities, we found out that they are quite distinct, and even with the simple random forest classifier, if you increase like sample size, you can reach almost 90% of accuracy. And we also try to investigate different metadata variables, whether they also can explain why profiles in different cities are different. And some of them really explain it, but not for all the cities. Like the ones you see here, especially like New York, I don't see quite well, but I think New York is the last one. They cannot be explained simply by the climate or by the density of population. This is really a good result in terms of accuracy, but I must tell you that if you add a sample which was not present in the data set before, this becomes really difficult and the accuracy drops because we have different challenge, which is called CAMDA challenge. It is part of ISMB, where we gave participants a possibility to identify like a mystery sample, which we infused in the metasub dataset. So this is still challenging. We also had to create bioinformatics pipeline, our in-house pipeline, because it was really hard to deal with lots of samples. And in the paper, we feature CAP2, which is core analysis pipeline 2. But here I want to highlight CAMP, which is core analysis modular pipeline, because we want to improve what we had. We want to create modular GitHub ecosystem where you only need like 5 steps to create module, which is super convenient for external developers, because we want to have our like informatics tool be quite broad, not only something that we have inside for our consortium. And here you can just clone cookie cutter example, which predefined module structure, which allows you to run unit tests or have automatically created documentation. And this is something we will try to complete within the next few years. of course, adding more and more samples into our pipeline. We didn't stop on that, and recently we created MetaSub Europe Society because we are constantly growing and it's really hard to operate. We kind of need several logistics hubs because currently we are sending all the samples in one place because we want to omit a technical bias, but it's really hard because of the amount of the samples we need to process. So in MetaSub Europe Society, we not only want to focus on the previous aims, we also want to go to the next level toward the global pathogen and AMR early warning system. So if you're interested to join, you can find me after the talk. And one more promotional slide, because MetaSub Krakow is hiring, and I really recommend. First of all, the city is amazing. Second, the MetaSub research is super fun, and the lab itself is super fun. So just take a picture of the QR code. And the last slide, is super important for me personally, because I'm from Ukraine, and probably all of you know what is happening now, and it has extremely bad impact on science in Ukraine. Like universities are getting demolished physically by shelling. Unfortunately, several very prominent scientists were killed by Russian troops, and maybe not every one of you realize that only female scientists can leave due to martial law. So the male scientists have to stay in the country, and actually even female scientists, they don't really want to leave because they don't want to abandon their families. And that's why we try to find some kind of remote opportunities to help the scientists in Ukraine. And it doesn't have to be something connected with huge money or funding. Even a simple supervision of students' works is really helpful. So if you know how to help, if you want to help, also please find me. And this is all from me. If you have any questions, please ask.
So thanks a lot. So we have some time for questions. There is one there.
Thank you very much. Slava Ukraini.
Героям слава.
So I actually have two questions. The first question is that you said that about 50% of your data was this dark matter, like you didn't know what it was. I wonder whether you did anything with it, like you assembled it, you called genes, and if you did, whether your assembled contigs or the genes you've called, you don't need to have, you don't need to have explanation which genes there are, but you just have the gene, the sequence. Did they match across different metagenomes, urban metagenomes?
Yeah, this is an extremely good question, and I think we should all work more on annotation-free methods for the classification of metagenomics data. We have separate article on that for MAX, for metagenome assembled genomes. I'm happy to talk about it more. I think this is still underdeveloped. In the main paper, I think we used MASH sketches to compare different samples because this is too much information. We don't want to lose it because, as I said, we still don't know yet whether it's a true unique urban microbiome or we just don't have enough information from, I don't know, commensal microbiome.
Yeah, or you could use, for example, K-MERS or something that,
yeah,
something abstract.
that tool I was mentioning, Metagraph, it's actually annotation free. Okay. And it can also do something which is called differential graph assembly. So you can basically create graphs from specific groups of samples, and then you can compare those graphs, and you can get the difference and to try to study it a bit more precisely. But for the main paper, we rather used this tool to give something outside to people. So you can search inside the index, but it can be used in many different ways. So this is a really good tool to check.
Cool. And if you don't mind, I will ask other questions, very quick question. So as far as I understood, you did sample different cities, also the different locations, right? Or it was the, yeah, so, and then I wonder if you cluster your samples, do they cluster per city or do they cluster per location? Like, do the subways in different cities look more alike, or it's like really more like per city clustering?
Several implications from that. First is quite obvious. Towards the equator, we have increased diversity of the species. So basically, we supported this claim, which was known previously. But we also saw that the coastal cities, like whenever you're close to some water reservoir, you will get more similar, like marine microbiome. But probably the easiest clustering we saw is basically based on the continent, but then the data starts to be too complicated to see the clustering visually, I would say. So even when I showed that slide with the accuracy, even when we know that it's easier, very easy to classify between cities, even when we take into account that core microbiome we found, it's common, but it's not abundant uniformly over all the cities. So some cities has really low abundant this core microbiome. So I think we still don't have enough resolution. We want to add this temporal plane because for that study, I think it was majorly like maybe 2 years of collection, but I think it's not enough. And we really want to go into metatranscriptomics, but this is even harder because it's more complicated in terms of technologies because I haven't talked about like quality control here, but it took enormous amount of time for us for quality control, for testing different library preparation steps, for different extraction. And of course, we had lots of troubles with storing the samples because the first year we actually asked people to ship on a dry ice, but it was a total failure because lots of shipment companies delayed and it basically ruined samples. But then we went to the Zymo RNA DNA shield and it works quite nice. So you can even store with the room temperature for a month and it will still be okay.
Thank you.
Okay, I think in the interest of time, we have to move on. We thank Paulina again. And the next speaker is Karishma Chugani. I hope I pronounce more or less well. And she's going to talk about genomics to face COVID-19 and future pandemics.
Can you guys hear me? Cool. Okay. Hi, everyone. My name is Karishma Chugani, and I'm visiting from Los Angeles, California. And to answer your question, yes, I'm very jet-lagged. I'm so grateful to be here at ECCB. It's my first time in Spain, and I love it already. Only been here for 2 days and want to move here already. I'm currently pursuing my PhD at the University of Southern California, and I'm pursuing bioinformatics research with Dr. Sergey Mangel. Today, I'm going to be talking about unlocking capacities of genomics for the COVID-19 response and future pandemics. So just wanted to mention, we were very fortunate to have our commentary published in the April special issue of Nature Methods. So feel free to check it out. I've posted the link above here. You can always reach out to me after the talk, or you have my name so you can find me online or LinkedIn. So in my opinion, I think one of the most important sentences written in our commentary is, during the COVID-19 pandemic, genomics and bioinformatics have emerged as essential public health tools. As a graduate student researcher involved in the field of bioinformatics during the unprecedented COVID-19 pandemic, I developed a greater sense of appreciation for genomics research as it brought the scientific community worldwide together for one common goal. And of course, this fight against the pandemic was definitely impossible without genomic and bioinformatic tools. These tools were the core of the efficient response from the beginning of the pandemic. And as an interesting fact, by the time when the World Health Organization declared COVID-19 as a global pandemic, hundreds of SARS-CoV-2 genomes had already been sequenced, characterized, and publicly available. And today, genomics and bioinformatics serve an essential role in fighting new and emerging COVID-19 variants. So here's a table of some online services with SARS-CoV-2 genome resources and analytics. We created this table to compile some different resources which are currently present, some of which include GESAID, which is a database for uploading assembled genomes, NextStrain for conducting phylogenetic analysis, and Outbreak.info, which consists of different variant reports. This could be a useful resource if you're looking to explore and learn more about available SARS-CoV-2 genomic resources online. So there's quite a few here, but I only named a few. COVID-19 definitely led to a mobilization of financial, scientific, and developmental resources in a record amount of time. As you can see on the figure to the right, the number of full-length genomes collected was highest for SARS-CoV-2 than any other virus such as HCV, HIV, and even influenza over the past. That number continues to rise every day as new variants emerge. And on the figure to the left, you can observe that depending on the continent, a varying amount of sequenced genomes were deposited onto the public database GESAID, which currently contains over 12 million SARS-CoV-2 genomes. As of earlier this year, according to the figure, Europe and North America had the highest number of sequenced genomes uploaded onto GESAID, whereas Oceania and Africa had the lowest number of sequenced genomes uploaded onto GESAID. These trends don't necessarily always quantify how much each continent is sequencing, but rather how each continent differs in publicly uploading this data onto databases such as GESAID. Now, when we take a look at the sequencing platforms which are utilized to sequence the genomes uploaded into GESAID and NCBI GenBank, you can see that the most popular platform for sequencing, as you might expect, is Illumina, which contributed to 80% of sequencing data. Interestingly enough, Nanopore is the second popular platform that contributed more than 10% of sequences and was three times more popular than PacBio. Based on our analysis, we found that there were indeed disparities in SARS-CoV-2 sequencing and that sequences are not collected evenly throughout the world. Gross domestic product, or GDP per capita, measures the economic output of a nation per person. The countries with the higher GDP per capita sequenced 100 times more on average than countries with the lower GDP per capita. As the income category increased from low all the way to high, the more genomes were sequenced per 1 million people. This leads to disparity, which can create blind spots in genomic surveillance, and as a result, can lead to key missing information for epidemiologists reporting the spread of new variants. However, something interesting to note, as highlighted in the figure, is that some African countries with a low GDP per capita were able to sequence a comparable number of viral genomes to middle and high income countries. As we dig deeper into why that could be, a possible reason why Africa has enhanced sequencing is maybe due to previous pandemics that took place in the African region, such as Ebola or malaria. Taking a closer look at the sequencing efforts in Africa, we can see that there are 4 countries highlighted. Although the 2 countries in blue, Gambia and Gabon, towards the top, have significantly lower GDP per capita than the countries in green, Tunisia and Egypt, towards the bottom, the former countries are actually more equipped with sequencing capacities and submitted more sequences. Africa provides a remarkable example of international cooperation that could be implemented in other parts of the world to improve pandemic response globally and perhaps to even eliminate disparities in sequencing. An alternative approach to monitoring COVID-19 epidemiology is to use wastewater facilities. Wastewater-based epidemiology can provide more balanced estimates of viral prevalence than clinical testing. That can be attributed to advantages in monitoring over clinically underserved communities and the ability to access asymptomatic cases. Wastewater monitoring and sequencing can detect outbreaks in early stages, which can help enable public health officials to make more informed decisions. Some of these decisions can include identifying hospital capacity and other important public measures such as quarantining, all of which is needed in advance. For example, monitoring through viral genome sequencing of wastewater samples allowed the identification of new COVID-19 variants in San Diego, California, up to 2 weeks in advance compared to clinical monitoring. Here you can see the time series for wastewater and clinical monitoring. Wastewater is represented by the blue dots in distribution, and clinical is represented by the gray dots in distribution. On the y-axis, there are 3 SARS-CoV-2 variants, epsilon, alpha, and delta. One can observe that alpha and delta variants were detected earlier in wastewater samples than in clinical ones, as shown in this figure. Creating a standard genome epidemiological sequencing system has many benefits. The immediate benefit of a standard sequencing system is that this can help improve the timeliness and accuracy with which emerging variants of interest and variants of concerns can be tracked. A longer-term goal is an improved ability to learn about the evolution during the emergence of novel and potentially dangerous variants. A truly global system of pathogen genome sequencing and analysis is likely to improve our ability to combat future pandemics. Currently, wastewater-based monitoring lacks the granularity of clinical diagnostic testing and cannot discern a particular area of an outbreak. This is due to the fact that wastewater treatment plant serves a huge population. Sampling at a higher spatial resolution within the sewer system, or maybe even at a building level scale, could potentially provide early indications of viral outbreaks and help monitor their progression. Finally, to summarize, some of the main contributions of genomics and bioinformatics for responding to the COVID-19 pandemic were that it enabled early warnings of the COVID-19 pandemic, shaped the effective COVID-19 response, enabled tracking COVID-19 geographical spread in real time, tracked SARS-CoV-2 genomic evolution, and also unlocked wastewater-based monitoring. Once again, I would like to thank my PI, Dr. Sergey Mangel, and my joint co-author, Sergey Knazhev, for their contributions, and of course, all the co-authors who helped make this work possible. Thank you very much.
So, questions? One question there at the back.
Hi, great talk.
Thank you.
So the wastewater approach to testing for variants can also be used to search for other viruses, right? So it doesn't have to be specific to COVID-19.
Yeah.
Is there any approach towards generalizing it, so to speak?
I'm not too familiar that has already been done, but definitely I think that is, I'm not sure what they've done in the past with wastewater. This is actually the first time I even knew that this was happening. And so I definitely think that could be a great approach to future pandemics or even previous pandemics that we're still fighting today. I think that could be a great way to track new emerging variants.
Thank you.
More questions? Well, I have one. So in this example, you show the wastewater monitoring. I understand these were like PCR amplification followed by sequencing with nanopore. So this was a targeted, so you knew you were looking for SARS-CoV-2. Mm-hmm. So what are your thoughts regarding, like sometimes like anticipating new pandemics, like maybe not a new pathogen, but not that we are already in an infection with COVID, but you may think that, something like a shotgun approach on wastewater could help identifying pathogens earlier on?
Yeah, I think definitely this is something that we have to keep up for sure. And definitely not only in, bigger countries, but even in smaller countries. We had some examples like in Africa that have a lower GDP per capita, but still, because they had more experience in previous pandemics, were able to sequence still. So I think it's wastewater sequencing, and that approach is definitely still, it's very relevant. I think it needs to be, we need to do more of it.
And regarding these examples in Africa, do you know about their bioinformatics was also more developed than the other ones because of the same reason?
Yeah, in those specific countries, we had, I think, more access and more resources to bioinformatics than other countries in Africa. And I think, once again, that goes back to what has happened in previous pandemics. So.
Okay. We have time for more questions. There's one there.
So as you mentioned that according to the GDP, there is differences in data collection. So while making general assumptions about the disease and the studies, how do you think that studies between countries can be comparable, especially when there's data differentiation?
Yeah, and that's something we definitely had to think about because, like I said, it's kind of tricky because not every country, not every continent has the same amount of resources, and they might not have the GDP per capita. So that's something we definitely had to think about, what's considered fair, I guess, to say, what would make it so that we can compare those differing countries. But I think we mostly just went off of what was publicly available on GESAID, but we definitely look into more specific scenarios.
Thank you.
Okay, thank you. So if there's no more questions, we thank all the speakers again, and thank you all for coming.